In this video, I'm going to revisit some key points from the oscillating particle model, which we abbreviated as OPM. So first up, the equations are a fairly key part of this model. There's two main ones that we worked out. The first is for the period of a spring. The capital T is used to represent period, and then that subscript S tells us that we're dealing with a spring. And so we have that equation where Ts equals 2 pi times the square root of m over k. We did a lot of working with proportions with this, so being able to pay attention to things like, if you want to double the period, how many times bigger do you need to make the mass? If you make the spring constant, that lowercase k that tells us about how stiff the spring is, if you make that bigger or smaller, what does that do to the period? And then again, being able to keep track of how that square root impacts how much bigger or smaller a change to the mass or spring constant does to the period. So then the other main equation we have is a very similar one, but it tells us about the period of a pendulum. And it uses Tp, where that subscript p means pendulum. And the period of a pendulum is just related to its length, and then G, which is the strength of the gravitational field, which we've been using as 10 newtons per kilogram or 10 meters per second squared. And those two units are equivalent. We also touched very, very briefly on this equation right here, which relates period to frequency. They're just the inverse of each other. This middle part is mostly useful when you want to get the period of an object that's moving around a circle with a constant angular velocity. With the oscillating particle model, you'll mostly use period equals 1 over frequency, and even that only shows up occasionally. So then, the major components of this model. One of the big things that you'll need to make sure you can recognize and interpret are position versus time, velocity versus time, and acceleration versus time graphs for an oscillating particle, so an object on a pendulum or an object vibrating on the end of a spring. And all of these graphs make nice sine waves. And if I go to a velocity time graph, as a reminder, when the slope of the position time graph is 0, that means the velocity is 0. So I need to have my velocity time graph. The zeros are going to line up with the peaks and valleys on the position time graph. So when I'm sketching graphs, I'll often draw in key points. Where does the velocity have to be a very large positive number? Where does it need to be a large negative number? And where does it need to be a 0? And again, that's based on the slope of the position versus time graph. And then I just play connect the dots, and I try to smooth it out into a nice sine wave. And in physics, we get a little bit sloppy about whether a graph is a sine or a cosine, because we can also think of a cosine graph as just a sine graph with a different intercept. And then I can do something very, very similar for the acceleration time graph. I'm starting by just making marks where the zeros are, and then I make marks where I've got a large negative or a large positive, and then I'm going to connect the dots. And really, just about any graph you're going to be asked to make for an oscillating particle on a spring or a pendulum is going to be a nice sine wave. Now, I also want to remind you that a few other graphs or diagrams that can be useful. One would be the LOL, to be able to think about the energy transformations as a pendulum swings or as a spring vibrates. Also, don't forget about free body diagrams and vector addition diagrams. And one of the big things that these can help reinforce is that the the net force on whatever's vibrating has to change. And we can even reason that out from the acceleration time graph. Because the acceleration changes, the net force must also change, since net force is mass times acceleration. So if you have a changing acceleration, you have a changing force. So these can help you reason out what's going on along with these motion graphs.